In Lecture 2, I reviewed the various structures we find in the universe, planets, stars, galaxies, and so on. But these are just the forms that matter takes, the way in which it's arranged. In this lecture, our aim is to look more deeply at the matter itself. Basically, what is the universe made of? As with many cosmological questions, this one also has a long heritage. The ancient Greeks, for example, referred to 5 elements: earth, water, air, and fire, and the celestial element, ether. And the Chinese also referred to 5 elements: fire, earth, metal, water, and wood, which in turn were related to deeper, more spiritual attributes of yin and yang. Now, it may come as an amusing surprise to learn that modern cosmology also recognizes 5 fundamental cosmic constituents. Here they are in decreasing order of familiarity: atomic matter, light, neutrinos, dark matter, and dark energy. So my aim in this lecture is to give you a feel for each of these substances, what their properties are, and what role they play in shaping the universe. So let's start with the most familiar one, atomic matter. We live in a world utterly dominated by atomic matter. You and I and the Earth are all made of atoms. It's now possible to actually photograph atoms. You can see them here, all nicely arrayed in neat rows. Now, atoms are famously tiny, but I think it's much more interesting to phrase it the other way around. We are mind-bogglingly huge collections of atoms. Now, to try to convey that, let's imagine living down in the atomic world so that atoms appear like these marbles. Let's imagine looking out at a human being. Each human cell is the size of a city. A big toe spans the United States. Looking up, our giant, made of marble-sized atoms, could reach up and almost touch the moon. When you say it this way, you can really feel just how remarkably creative Darwinian evolution is. After 4 billion years, it's created a mechanism to assemble structures so huge out of units so small. And these structures actually work very well. Let's now briefly look a little deeper at the nature of atomic matter. First, working up in scale. If the conditions are right, atoms can stick together to make molecules, and ultimately much larger things like chairs and people, or even planets. However, atoms aren't themselves fundamental. They're made of yet smaller things. Famously, atoms resemble in some sense miniature solar systems, in which lightweight electrons orbit around a tiny heavy nucleus, 100,000 times smaller. The nucleus is also composite, containing protons and neutrons, and these in turn are composite, each containing 3 quarks. Currently, we think there are no deeper levels. Quarks and electrons are the fundamental building blocks of atomic matter. Now, something we really can't perceive is the incredible dynamism of the atomic world. Everything is moving around at blurred speed. Quarks orbit within protons 10 to the 24 times per second. Protons orbit within nuclei 10 to the 20 times per second. Electrons orbit within atoms 10 to the 15 times per second. If an electron's orbit took 1 second, then for me to say hello would take 30 million years. But these are all motions within atoms. What about the motions of the atoms themselves? Well, not surprisingly, atoms are in constant motion. Even in solids, where the atoms are stacked shoulder to shoulder, they nevertheless jostle back and forth like tiny pinballs caught in a pinball machine. Now, although we don't perceive this motion directly, nevertheless, we are aware of it indirectly as temperature. Stated simply, as temperature increases, atoms and molecules move faster and faster. And this makes perfect sense. Imagine putting energy into an object, for example, heating it. Where does that energy go? Answer, it goes into the kinetic energy of the atoms and molecules. They speed up. As you might imagine, in the melee of atomic motion, not all atoms move at the same speed. There is a well-defined spread of speeds called the Maxwell distribution, after the Scottish physicist James Clerk Maxwell. For hotter objects, the distribution spreads out and shifts to higher atomic speeds. In the other direction, there is a lowest possible temperature when all atomic motion ceases and everything is quiet in the atomic world. This lowest temperature occurs at minus 459 Fahrenheit or minus 273 centigrade, or, to use the physicist's temperature scale, it's 0 degrees Kelvin. It's also called absolute zero. In these lectures, I'll be using this temperature scale that's named after the English physicist Lord Kelvin. Now, for high temperatures, like the centre of the sun, it's almost the same as centigrade, while at low temperatures, kelvins are 273 larger than centigrade. Your body, for example, is about 310 Kelvin, or 36 centigrade. Now, one of the reasons that scientists use the Kelvin temperature scale is because it immediately tells us the average kinetic energy of the particles. This is extremely important because it tells us the violence of the collisions. Now remember that atomic matter contains a sequence of structures: quarks, protons, nuclei, atoms, molecules, objects. But the forces that maintain these structures are not infinitely strong. And if the structure is smacked sufficiently hard, it'll break. So this diagram shows the temperatures at which these various structures disintegrate. So we're all familiar with the breaking of relatively weak intermolecular forces because objects melt and then boil at a few hundred degrees. Also, big molecules, such as proteins, break at modest temperatures, on your stove, for example, when you cook food. By about 1,000 or 2,000 degrees, even small molecules, like water or carbon dioxide, are broken because the interatomic forces involving the outermost electrons aren't all that strong. Starting at about 10,000 degrees, the outer, most weakly bound electrons are bashed off the atoms in a process called ionization. And this creates a rather unusual kind of gas called a plasma that contains positively charged ions and freely roaming electrons. By about 1,000,000 degrees, even the innermost electrons are lost, and the gas is now said to be fully ionized. It's just bare nuclei and free electrons zooming around at incredible speeds, ricocheting off each other. Well, let's continue to higher temperatures. Between 100 million and 10 billion degrees, atomic nuclei are smashed into free protons and neutrons. And at the enormously high temperature of 1,000 billion degrees, even protons and neutrons are smashed into quarks. Now, nowhere in today's universe do such extreme temperatures exist. But in the first microsecond after the Big Bang, everywhere was above this temperature. And it was too hot for any of these structures to exist. And so, as we'll learn in Lecture 28, at that time, only the fundamental particles were present. Now, in today's universe, almost all the atomic matter is to be found in stars and hot intergalactic gas, where it's too hot for atoms to survive. And for this reason, astronomers tend not to use the term atomic matter, but instead they use the term baryonic matter, which is just a fancy name in this context for protons, neutrons, and electrons. But in these lectures, I want to keep jargon to a minimum, and so I'll continue to refer to this cosmic component as atomic matter, even though we know actual atoms themselves are fairly rare. In fact, overall, the universe is a pretty inhospitable place. with only 0.01% of the atomic matter sufficiently cool for atoms to actually survive. And if you want to find complex molecules, then only a few planetary surfaces have the necessary gentle conditions. So, when you look at things this way, we live in an exceedingly unusual place. Perhaps a billionth of the cosmic atomic matter takes the form that we see around us. Let's finish talking about atomic matter by asking, how much of it is there in the universe? Well, on average, it amounts to just 1 proton and 1 electron per 4 cubic meters. That's the size of a large car. Now, of course, there are a lot of cubic meters in the universe, and added up, the total in the visible universe is about 10 to the 51 kilograms, or 10 to the 21 times the mass of the Sun, a huge amount. However, this is only about 4% of the total. The other 96% are in the other cosmic components. So let's turn now to the second most familiar one, light. There is, of course, an astronomical reason that we're so familiar with light. We've evolved under the bright light of a very nearby star, the Sun, and so we have eyes that can see. But what actually is light? There are 2 ways to think of it. First, as an electromagnetic wave, a rapid ripple of electric and magnetic fields that moves through space exceedingly fast, 300,000 kilometers per second, 7 times around the world in 1 second. The electromagnetic spectrum simply orders these waves by wavelength. From long to short wavelength, we have radio, microwaves, infrared, visible, ultraviolet, X-rays, and finally gamma rays. The range in wavelength is huge, from radio waves longer than football fields to gamma rays smaller than atoms. Light sits in the middle, with a wavelength about 200 times smaller than the width of a human hair, with the rainbow sequence of colours, red, orange, yellow, green, blue, violet, spanning the wavelengths from 700 to 300 nanometers. Now, the second way to think of light is as a tiny particle called a photon, which also has a wave-like character. This view of light was promoted by Einstein in 1905 when he realized that photons with shorter wavelength carry more energy. Now, although the energy of individual photons is imperceptible to humans, they can pack a real punch in the atomic world. So, for example, ultraviolet photons can smash large molecules, X-ray photons can smash atoms, and gamma-ray photons can smash nuclei. Okay, let's consider the important question of how photons are created. The most important mechanism is the one that makes the sun shine. Its surface is hot, and hot things glow. And the reason they do is all to do with that constant atomic motion. Every time a charged particle collides and is deflected, its electric field becomes kinked, and that kink moves off at light speed. A photon is created. If the collision is more energetic, so is the photon. So with that in mind, let's return to that diagram of the spread in atomic speeds in a gas. In the melee of collisions, some will be gentle and glancing, while others will be violent and head-on. So obviously then, the photons generated by all those different collisions will also span a range of energy. They have what is called a thermal spectrum. There's 2 more things I want to say about thermal radiation. First, hotter objects have more energetic particles which create more energetic photons, so the spectrum shifts to shorter wavelengths, bluer light. These examples span a small range of temperature from sun-like stars to somewhat hotter stars. But it's true outside this range. Gas at 1,000,000 degrees glows in X-rays. Gas at 1 billion degrees glows in gamma rays. Now, the second important point is that hotter gases glow more brightly. You can see this from the height of these curves. The effect is actually very dramatic, with the energy produced increasing with temperature raised to the fourth power. So doubling the temperature of a gas makes it glow 16 times brighter. Now, there's a second way that photons can be created. It happens when electrons jump from an outer orbit to an inner orbit inside atoms. When this happens, the photon created carries off exactly the energy difference between the two orbits. Now, for reasons I don't have time for just now, electrons moving inside atoms have only a few possible orbits. So the photons created in this way have a very few specific energies or colours. In a spectrum, they show up as spikes of pure colour, and they're called spectral lines. And they give many nebulae their spectacular hue. Now, there's an opposite process. Photons can be absorbed by atoms when they force an electron from a lower energy orbit to a higher one. This happens in the atmospheres of stars, and so the spectrum of the Sun, for example, while overall it has a thermal shape, also has a number of absorption lines where these particular photons have been absorbed by the atoms. Now, these spectral lines, both emission and absorption, are extremely important to astronomers because they reveal all kinds of properties about the object that's emitting the light. What it's made of, how hot it is, what its pressure is, and if it's moving. You see, ultimately, we're marooned on this planet, so we're utterly dependent on light to bring information to us. It rains down from the sky and brings with it an amazingly rich biographical text about the objects that made it. The astronomer's job, of course, is to read that text and learn about the objects. Let me finish this discussion about light by asking how much of it is there in the universe. So, if you average over everywhere, you find each cubic meter contains 400 million photons. So relative to atomic matter, that's 1 billion photons for every proton or electron. Now, as we'll find out in lecture 13, almost all of these photons were made in the Big Bang. And they're now invisible to us because they're in the microwave part of the spectrum. They are the famous microwave background. All the stars in all the galaxies shining for 14 billion years haven't begun to compete with the fantastic glow created by the hot gas in the Big Bang. But of course, microwave photons, with their long wavelengths, have very little energy. So today, they add up to only 0.005% of the total cosmic contents. That's just a teaspoon out of 25 gallons. So photons are very numerous, but a very minor component in today's universe. Now let's turn to that third cosmic constituent, neutrinos. I actually don't have much to say about these, and with a couple of exceptions, they don't play a major role in the cosmological story. You can think of neutrinos as similar to photons, almost no mass, pure energy travelling at the speed of light and spinning. But unlike photons, neutrinos hardly interact with matter at all. In fact, right now, billions upon billions of neutrinos are passing right through your body, and not a single one is colliding with any of your atoms. And this makes them extremely difficult to detect. But with great care and using huge experiments like this one, physicists have been able to detect neutrinos coming from astronomical objects such as the Sun. But the Big Bang made enormous numbers of neutrinos, roughly as many as photons of light. And just like we have a cosmic microwave background of the Big Bang photons, We also have a cosmic neutrino background of the Big Bang neutrinos. But also, just like the photons, these neutrinos have very little energy. And so I'm afraid to say that they are likely to go undetected in the foreseeable future. Now, in Lecture 25, I'll come back to the role of neutrinos in the first second after the Big Bang. It turns out that without them, the universe and life would have been fairly different. So ultimately, they are actually quite important. The last two cosmic constituents, dark matter and dark energy, are much more enigmatic. But together they comprise 96% of the total. So let me briefly introduce them to you now, and then I'll come back and discuss them in more detail in Lecture 9. Now, currently, we really don't know what dark matter is actually made from. The best guess is that it's a kind of subatomic particle made in the Big Bang, a bit like a heavy version of a neutrino, weighing maybe a few times the mass of a proton. Dark matter particles are like neutrinos in that they barely interact with normal atomic matter, which is why they're so difficult to detect. But when they are, or if they are, finally detected, and there are several teams around the world trying to do just that now, it will be an incredibly important Nobel Prize winning discovery. So, how do we know that dark matter exists? Well, from its gravitational effects. As we'll see in Lecture 9, there are now many observations that reveal the presence of much more mass in and around galaxies than just their stars and gas. Dark matter seems to be spread with an intermediate level of clumping, not as uniform as the cosmic microwave background photons, but it's not as clumped up as the atomic matter in stars and galaxies. Instead, we think dark matter forms giant halos that surround galaxies, and these halos provide a framework into which atomic matter falls and makes galaxies. Overall, in the universe, there's 6 times more dark matter than atomic matter. But because it's spread out so much, its density at any given place is very low. Within the Earth's volume, for example, you'll only find about a kilogram's worth of dark matter particles. So you can see why it's proving very difficult to detect. Our final cosmic constituent, dark energy, was only discovered in 1998. And just like dark matter, we don't know what it is made of, and its existence has been inferred through its gravitational effect. For reasons we'll get to in Lecture 12, the gravity of dark energy actually makes the expansion of the universe speed up, and it's this speed up that was measured for the first time in 1998. The best guess is that dark energy is a tiny residual energy associated with space itself. And for this reason, it's sometimes called a vacuum energy. The energy is very slight, just 5 hydrogen atom masses per cubic meter. But when you average over everywhere, it's the dominant component, coming to 73% of everything. So now you know the 5 cosmic components, let me just review their relative amounts. So first, when averaged over the whole universe, you find a total density of about 5.8 hydrogen atom masses per cubic meter. That's roughly a grain of sand within the Earth's volume. So the universe is, on average, extremely empty. Of this density, dark energy makes up 73%, then dark matter at 23%, then atomic matter at 4%, and light and neutrinos a tiny 0.005 and 0.0034%. Now these numbers are measured, how these numbers are measured is quite a story, and I'll come back to them later in Lecture 26. So until then, just trust me that these numbers are about right. Now here's an interesting question. Has this density and its fractional makeup always been the same? The answer is a very definite no. Both of these things change. First of all, as the universe expands, its matter content gets spread out, and so the average density drops, as you can see in this diagram, which has exponential axes with density upwards and cosmic size, or expansion, going to the right. So we have a decreasing line for matter, and that includes both atomic and dark matter. Now, this logic doesn't apply to dark energy, because dark energy is a property of space itself. Its density is constant, therefore, even though the universe expands. So dark energy's density follows this horizontal line. So you can see that although today dark energy dominates the total density, about 4 billion years ago, matter and dark energy had roughly equal densities. And at earlier times, matter was dominant. In fact, in the early universe, dark energy was completely insignificant. Well, what about light and neutrinos? Their line is shown here. Just like matter, their number per cubic meter decreases as the universe expands, and they thin out. But there's an additional effect that we'll come to in Lecture 7, called redshift. And this reduces the energy of each photon and neutrino, so their line falls even faster. And because of this difference in slopes, you can see that the matter and radiation lines actually cross near 60,000 years after the Big Bang. Before this time, radiation is actually denser than matter. For example, 10 seconds after the Big Bang, matter is about as dense as the air we breathe, but radiation is 200 times denser than lead. As we'll see in later lectures, when the dominant component of the universe changes, so do many other things. The character, if you like, of the universe shifts. And to keep track of these different characters, cosmologists divide cosmic history into the radiation era, the matter era, the dark energy era, depending on which component is dominant. Now, if you're philosophically minded, you'll be pleased to hear that although I've described 5 different components, really they're all different forms of a single entity, mass energy. Einstein's most famous equation, E equals mc squared, tells us this. All forms of energy and mass are interchangeable. They're deep down the same thing. The conversion constant, c squared, that's the speed of light squared, is a huge number. So you can think of matter as an extremely concentrated and stable form of energy. For example, if we took 1 kilogram of matter and suddenly convert it into energy, we get the equivalent of a 10 megaton city-destroying hydrogen bomb. So matter is incredibly concentrated energy. Now, the equivalence of mass and energy is what allowed me to intercompare the densities of the 5 components. So although one speaks of vacuum energy density, if we divide by c squared, we find its equivalent mass density, 5 hydrogen atom masses per cubic meter. Now, a crucial point about either mass or energy is that they generate gravity. They pull. So out between the galaxies lies a pervasive gravitational field generated by all the cosmic components. In a sense, one might actually view gravity as a 6th cosmic component. However, gravity has a very unusual character not shared by the other components. As we'll see in Lecture 11, its energy is negative. So I want to end this lecture with a rather stunning property of the universe. Let's just see how much mass and energy is present in the visible universe. Using 5.8 hydrogen atom masses per cubic meter for the average density and a radius of 14 billion light years, you get the mind-bogglingly huge mass of 10 to the 53 kilograms, which is about the same as 100 billion galaxy masses. The universe contains a huge amount of mass energy. Where did it all come from? Well, careful. we've not yet done with the calculation. We've forgotten to add in the negative gravitational energy. When you do this, you get a huge negative gravitational energy, which, if we divide by c squared, is equal to minus 10 to the 53 kilograms. It's exactly the same as the positive mass energy of the 5 components. So the total mass energy of the universe is mass energy plus gravitational energy equals 0. The universe sums to nothing. This has to be one of the most stunning modern cosmological results. It also has a poetic and aesthetic power comparable to what one associates with traditional, spiritually based cosmologies. This result also gives us an insight into how the universe might have come into being. Perhaps it came from nothing. As we'll need, all we need is a mechanism to split nothing into huge amounts of positive matter and energy, all bound together by an equal amount of negative gravitational energy. As we'll see in later lectures, it is inflation that provides exactly this kind of mechanism. So stay tuned.